Oxidation numbers are a simple way for us to determine if electrons are being moved around in a chemical equation. And if electrons are being moved around in a chemical equation, that tells us that the chemical equation is a redox reaction. An oxidation number is the apparent charge of an atom if the electron pairs in a covalent bond belonged entirely to the more electronegative atom. For this, let's look at water as an example. Oxygen has an electronegativity of 3.4, where hydrogen has an electronegativity of 2.2 from our periodic tables. Now, based on what we know about oxidation numbers so far, this means that the pair of electrons that is represented by this bond is actually going to be given completely to the more electronegative oxygen. So oxygen would actually have 8 electrons around it, and hydrogen would have none. Oxygen normally has 6 electrons in its valence shell. Now it has 2 more. We give it an oxidation number of -2. Hydrogen normally has 1 electron in its valence shell. It now has none, and so we give it the oxidation number of +1. Notice the difference in oxidation numbers. We say -2 versus in an ion we say 2-. Oxidation numbers, the sign comes before the number. In ions, the sign comes after the number. If there's any change to an oxidation number, either an increase, which means oxidation, or a decrease, which means reduction, then we are dealing with a redox reaction. When iron goes from an elemental form to a 2+ ion form, we are undergoing oxidation because the oxidation state of this iron was 0 and now it is +2 because of its charge. An increase in oxidation number means oxidation. Oxygen has an oxidation state of 0, and now it has an oxidation state of -2. It has decreased its oxidation number or oxidation state, and therefore it is undergoing reduction. Here are our rules for assigning oxidation numbers. The first rule is that the oxidation number of any free element is 0. Chlorine, Cl2, as a gas, has an oxidation number of 0 because the electronegativity between the 2 chlorine atoms is equal, and there would be no shift of electrons to the more electronegative element. An atom like iron also has an oxidation number of 0. Oxidation numbers for monatomic ions is the charge of the ion. A sodium ion in solution has a 1+ charge. Its oxidation number is +1. A chloride ion in solution has a charge of 1-. Its oxidation state is -1. Hydrogen has a charge of +1 in most compounds unless it's a metal hydride like lithium hydride. Because in lithium hydride, hydrogen has the higher electronegativity, it gets the oxidation state of -1, and lithium would get the oxidation state of +1. Oxygen has a charge of -2 in most compounds except in peroxides like sodium peroxide. And in peroxides, oxygen has an oxidation state of -1. The sum of oxidation numbers of all atoms in a substance must equal the apparent charge of the substance. So if we have an ionic compound, all ionic compounds have a charge of 0. Oxygen has a oxidation number of -2. Magnesium has an oxidation number of +2, and the oxidation numbers also balance to make 0. If we have a phosphate ion, which should say PO4 3-, we have to have an oxidation state balance. So oxygen has a -2, which is 8, minus for your total oxidation state, and therefore phosphorus must have +5 because +5 and -2 times 4, -8, makes -3. Let's look at a few examples to help you assign oxidation numbers. We're going to look at nitrogen in N2O. In order to do this, we follow our rules that oxygen has a -2 oxidation state. There's 1 oxygen for a total of -2 for the oxidation state. The total charge of our molecular compound is 0, and my oxidation states must also equal 0. So I therefore must have a +2 oxidation state from nitrogen. There are 2 nitrogens, so each nitrogen has a +1 oxidation state. Now let's look at nitrogen in NO3, 1 minus. Again, oxygen has a -2 oxidation state. There are 3 of them, which gives us a -6 oxidation state. This has to total -1 because the charge of my ion is 1 minus. That means nitrogen must have a +5 oxidation state. There's only one of them, so this nitrogen has a +5 oxidation state. If we look at carbon in ethanol, we can assign hydrogens +1 and oxygens -2, which gives me a total of +5 -2 +1, which actually gives me a total of +4. Now, we know that this has to equal 0 because the charge of ethanol is 0. We must have a -4 oxidation state for carbon. There are 2 carbons. Each carbon must have a -2 oxidation state. In biology, you've probably been told that when glucose is used in cellular respiration, it is undergoing oxidation to turn into carbon dioxide. Now that we understand oxidation numbers a little better, we can prove why glucose turning into carbon dioxide is oxidation. Let's assign oxidation numbers to glucose. -2 for oxygen, +1 for hydrogen. If we total those up, -2 times 6 is -12, and +1 times 12 is +12. And the total must equal 0, so carbon must equal 0. If we look at carbon dioxide, we have -2 for oxygen. There's 2 of them, so that gives me -4. Again, the total must be 0, so I must have +4 for carbon, and there's only one of them, so +4 is carbon's oxidation state. Carbon is going from an oxidation state of 0 to +4, and if there's an increase in oxidation state, it means we are undergoing oxidation.